All right, we're going to do this again. Video number 2, we are going to do the TIG lecture. So I'm probably on a trip again, so let's do the TIG lecture. We'll try it again. Hopefully the MIG one worked for you. So, gas tungsten arc welding, also known as TIG welding. Lots to talk about on this one, but here we go. So the TIG welding process uses a non-consumable tungsten or tungsten alloyed electrode. So the filler metal is added by hand or by a cold wire feeder. So you got your torch in one hand, got your wire feeder in the other, typically just a piece of 36-inch rod, filler rod, and your foot is typically doing the heat control. So you have 3 different things going on all at the same time, so it takes a bit of practice. They say you got to be a drummer to be a TIG welder, but it's because you got these 3 different coordinating things going on all at the same time. But we did some oxyacetylene welding, so you kind of got a feel for it there. Now we add the foot control when we get into TIG welding. So good foundational stuff here. So a little bit of history about TIG welding. It had its beginnings from an idea in the 1890s, and it dealt with arc welding under an inert gas atmosphere. So the TIG process was refined in the 1940s, basically by Northrop Aviation Company, because they wanted to find a way to join magnesium, aluminum, and nickel. TIG welding actually also is kind of what started before MIG welding. They learned from TIG that, hey, what if instead of tungsten we fed a wire through there instead? But lots of other things happened. So TIG welding was a little bit before then, and in the photo here you can see a pretty cool archaic looking torch setup of the original torches that were made to do TIG welding. So there's a bunch of name variations used for TIG welding. So TIG, probably the most common thing that people use, stands for tungsten inert gas. AWS initially referred to it as tungsten inert gas or TIG in a publication, and so that's what really set its name to be widely accepted. But GTAW, or gas tungsten arc welding, that's the official name supplied by the American Welding Society. When we do code work, when we do anything else, we need to say gas tungsten arc welding. That's the formal best way to do it. Another name that people still use is called HeliArc. Well, that's a trade name by a manufacturing company called ESAB. So HeliArc was insinuated that you used helium to do this, because when the process was first invented, they used helium for the shielding gas completely. Well, now we've learned, helium's a limited resource. If we run out of helium, MRI machines don't work. And again, helium we can't manufacture or extract. It is a limited resource, so we have to be very careful on how much helium we use. So helium balloons, shouldn't be buying them anymore. We got to save helium because we need it to weld things, and the medical industry really needs it. And even in the welding industry, we want to try to find ways to not use helium either, because there are other solutions. But sometimes helium might be the best for a given application. But again, it's expensive, and we sometimes want to shy away from it. So some of the old machines back in the day in the 1940s, they were just gigantic monsters. And over time, they got a little bit smaller. But in 1976, a major event happened, and the square wave idea of an AC waveform came about. We're going to be talking a lot more about wave shapes, and we're going to understand them a little bit more. But for now, to understand, in 1976, this patent came out and completely changed the way we AC TIG weld aluminum. Totally different world. So we'll be talking about what that stuff does. Today, lots of different machines. Obviously we got the blue stuff on here, but that synchro machine in the corner that stuff's gonna die. That's the old technology today. The new stuff is the dynasty type technology, which is all we have here at the lab at ASU. That old school synchro technology, don't even use it anymore. It's really phasing out, simply because the benefits we get that we're going to be talking about in TIG here from the advanced machines just so far outweigh what the old machines could do. The old machines are dying because the new ones are just that much better, and that much better technology. Make us more productive and everything else. So some of the TIG applications and markets, well, you can find TIG in any weldable metal. If it can be welded, we can TIG weld it. We could TIG weld gold if we wanted. It'd be very expensive, and the filler rod would be pretty expensive, and any waste would be extremely expensive. But any weldable metal can be welded with TIG, because TIG is the most metallurgically pure of the welding processes. So I can even go so far as to maybe slice a thin piece of my sheet stock for the metal I'm welding together and use that as my filler rod. maybe not the best, because some of the filler rods have a lot of great properties and alloys to really make a stronger weld, because the weld itself is a very unique metallurgical event that's happening to that base metal. But theoretically, I can just take my base metal and use it as filler metal in TIG if I have to. So where do we find it? Every industry: motorsports, food processing, aerospace, tube mills, petrochemical, plumbing, piping, sheet metal. TIG welding is everywhere. You know, even nuclear facilities, that's how they do a lot of their pipe TIG, because it's so much cleaner and so much more pure. They can control the quality of the weld significantly. Food processing, huge. Think about our gallon of milk. We come from the cow, we go into all the stainless steel welded processing facility, and all the inside of those pipes have to have very smooth surfaces so that bacteria and things don't get caught inside that pipe and therefore poison all the batches of pipe, and everybody gets sick buying the milk. So TIG's a very good, clean, smooth welding process. So again, any metal. You can see the list here, it goes on, you know, but any weldable metal can be welded with TIG. So some of the advantages of the process: high quality, pinpoint control and precision, beautiful weld beads, provided the operator can do that. No sparks or spatters. If you have sparks or you have spatter coming off of a TIG weld, something's wrong. You've got a contaminant somewhere. You need to clean that part. No flux or slag. So again, there is an exception in the flux world. They make some unique fluxes out there in TIG welding that are like heat barrier fluxes. So you might be in a unique application. You don't want heat to transfer across the part for some reason, and they actually use these unique flux dams, and you kind of put it around your weld zone where it needs to be, and it'll kind of trap the heat in that zone on stainless steel. So that would be the only place you might see flux with TIG welding, but otherwise there's no flux produced, there's no slag produced. It's clean, smoke-free, spatter-free. No smoke or fumes. Again, if you do have smoke coming up, it means you're burning something. And again, we can weld more metals and alloys than any other welding process. One thing about smoke or fumes, a lot of people in the automotive world think that they want to take brake cleaner to clean something before we weld with TIG weld it. So TIG is being the cleanest process. We have to clean our parts, and you'd think that brake cleaner would be a great thing to clean parts, but it's actually extremely dangerous. Never use brake cleaner, because it leaves a residue, and then when that residue burns, it actually creates chlorine gas, and now you got a problem. So you can literally pass out. There's been articles out there that people have done that, and they've actually passed out in their garage wondering what happened because they were breathing chlorine gas. Lucky they didn't die. So very careful. Always use the right cleaners. Cleaners being, we got to get rid of oil, grease, dust, dirt, and debris off of our TIG weld, because that base metal's got to be very clean to start. So typically people will use acetone, but acetone will actually smear some of the things on there and leave a residue. There's actually one product out there that I know of. It's called Tri-Zero by LPS Laboratories. It leaves no residue, and it's obviously pretty nasty stuff. It's actually so nasty that it's illegal to use in California, so it must be good. But the Zero Tri from LPS Laboratories is the best cleaner degreaser that you could use if you're doing highly critical applications. Acetone might work. There's other cleaner degreasers out there. Another very good one is Fantastic. Off the shelf, the soap Fantastic. You can even dilute it down a little bit, but you have to rinse it away. 409 doesn't work, Simple Green doesn't work, but for whatever reason, the formula in Fantastic works really great on aluminum. So, enough about cleaning your weld before you weld it. So the gas tungsten arc welding system. We use a lot more components. If you recall, in the shielded metal arc welding or stick welding, there wasn't very much to it. But in gas tungsten arc welding, we start basically with a shielded metal arc or stick welder, because it's constant current output, and we add all these other components. You got your regulator flow meter, because we need our argon or inert shielding gas. We need our power source that's constant current. We might need a cooling system because we're using a water-cooled TIG torch. We need a remote control that's typically a foot control, but if there's all kinds of different hand controls that can be used. We need our work clamp, our work cable. We need the gas to get into the torch. We need the power to get into the torch. We need the coolant to get into the torch. And we need the coolant to get out of the torch. So lots more components in a TIG system, so that definitely increases the price of a TIG system. But great welding process. So our work clamp and cable, Again, it completes that circuit to make the welding possible. Our coolant system keeps that torch cool. But there's some very important things about coolant systems for TIG welding. Number one, you have to use either the low conductivity coolant from the manufacturer. If you use that, it's good for about a year. If you don't use that, then you need to use distilled deionized water. And if you put that in the system, you need to change it every 6 months. The reason for deionized water is in TIG welding, and we're going to talk about arc starting methods, but we use high frequency, and high frequency takes its path to earth ground however it wants to take. And if we're using just tap water is very conductive. So that high frequency, instead of jumping across the arc to start my arc for me, it might travel down that water line and find earth ground through the case of the machine easier than where we want it to go to help me strike that arc. So low conductivity coolant by the manufacturer or distilled deionized water is all that you can use. People will use automotive antifreeze. That's suicide on a coolant system because automotive antifreeze has clogging agents in it, and those clogging agents go to the head of the torch, and up in those little tiny areas in the head of the torch, it'll see that as a leak, and it'll start to build up those clogging agents in there, and now we have a destroyed torch. It's not getting cool. I'm out $300, $400, $500 for a new torch. So automotive antifreeze, horrible thing to use in a TIG welding coolant system. Another story real quick too, an environmental story. Companies will have in the past where they literally just run tap water through their torches and put it down the drain. I had a company here in Phoenix, that's what they were doing. They were getting a lot of porosity in their aluminum welds. And it happened mostly in the morning and mostly after lunch. Why? Because that torch was just sitting in the shop, cold water was flowing through it, and so they were getting condensation up in the side of the torch head on the copper parts that were being cooled, and so when they would be welding, they'd be introducing hydrogen into their weld. Well, hydrogen equals porosity in aluminum, and it equals suicide in your weld. So once they bought coolant systems, put the right stuff in it, all those quality issues went away, and being in Arizona, it's probably a little more environmentally friendly to make sure they weren't just taking that water and dumping it down the drain. I actually gave them a hard time on that as well to help influence their decision to buy coolers. But anyway, side story. So the foot pedal, fingertip control, does a lot of functions for us. When we're TIG welding, there's a sequence of events that occurs. So when I first hit that foot pedal, it'll initiate the gas. It'll turn on the shielding gas. And then it'll want to, and I can change how long it delays, then it will want to start the arc. And basically the way, so hit the foot pedal, gas comes on, we start the arc, we ramp up to welding speed. We get to the end of the weld, we have to crater off to the end of the weld. We can't just instantly shut it off. We want to gradually shut it off so we don't get a crater or a crater crack that could lead to a weld failure or a discontinuity. But we taper it off, and then we shut off the arc, and then we need post-flow to continue running, and then that post-flow turns off. So there's this sequence of operations that happens, that has to happen in TIG. You can automate this sequence, or we typically are just doing it with our foot pedal. And the way that the foot pedal works is if I set the panel of my machine at 100 amps, when I floor that foot pedal, I get 100 amps. I might have a 300 amp machine, but I'm limited by what I've told the dial on the machine to max out at. So if it's at 100, I got a pretty good 0 to 100 range in my foot pedal. If I go to 300, that slight move on my foot pedal now is a lot more amperage change. So you want to get that down to around the zone that you need to maximize your operating at, and maybe that 80% level is good. So if I was welding, let's just say at 80 amps to make the numbers easy, if I had to weld at 80 amps, I'd want my panel set at 100 amps, so I had that little extra oomph if I needed it. Just depends on the operator and how you're doing things, but that relationship between the front panel and what maxes out on the foot pedal is important to remember. Shielding gas, of course, very important. It's an inert gas to dispel the other gases that, they don't just, inert gases don't mix with other gases, so it protects that part significantly. In the illustration, you can see two torches. The one on the left is just a normal collet body. That's what we're using here in the lab, just because it costs less money and it doesn't get gummed up so easy when everybody's learning how to TIG weld. But you can see how we're literally using smoke and mirrors in this image, where the smoke, just the gas coverage is just kind of, it's there, it's doing an adequate job, but you can see there's a lot of potential spots for inadequate gas coverage. If you look at the image on the right, where it comes out at a nice lamellar flow, that's using a gas lens, and that gas lens filters that gas, that shielding gas, to give very good coverage, and you can see it in that image night and day between the two. So gas lenses are a great tool to use in TIG welding to help your shielding gas to protect that weld area. It also protects that tungsten from impurities, and some of those impurities are nitrogen, oxygen, hydrogen, any of the other gases, especially the reactive gases that could destroy our part. The shielding gas improves the color of the weld bead. So a common misconception in the welding world is that your weld bead, you can look on the back side and see that there's color change and say, oh, I got penetration on that part. Well, how did you really? All that tells me is that you heated the back side enough so that the atmosphere attacked that surface and oxidized that surface, and each different shade of color tells you what temperature the surface of that material was when it got out of that argon environment and the atmosphere attacked it. So when I'm doing a nice stainless steel weld and there's a nice straw color, that means that straw color, it's actually a level of oxidation on how hot that stainless steel was when I lost my argon bubble. So titanium, for example, has a very strict standard that it cannot lose its argon shielding until it is below 500 degrees Fahrenheit. If it's above 500 degrees Fahrenheit, that oxidation will make that titanium weld fail, and it just won't work. But as long as it's below 500 degrees before we remove the gas, titanium's good to go. So the improvement of the color of the bead really means that the argon shielded that part long enough to cool so that that surface did not get oxidized from the atmosphere. So if I'm in an argon bubble, welds are going to be shiny clean. But typically we're not welding in an argon bubble, we're out in a shop, so we need to make sure we have good adequate gas coverage so that as we move along, that weld behind us isn't so hot that it gets overly oxidized on the surface. So some of the most common gases used in the industry are both argon and argon-helium mixes. But again, we want to try to minimize the use of helium. Argon usually does more than an adequate job for everything you do. So the gas tungsten arc welding torch, you don't need to remember any of this stuff, but just kind of a nice cutaway to see how the collet body and the threads all fit in there. But the most important thing about a TIG welding torch is the order that you put all of the parts together. So it's very important that we put the collet body threads in first. So we need to have that back cap off and put that collet body in first so that it stops, it's all the way down. And that's the mistake that too many people have when they take off their nozzle. They loosen up that collet body, and then now you don't have the travel distance in your back cap to ensure that it makes connection with the collet so that that collet can then crimp onto and hold that tungsten in place and carry the current to that tungsten properly. So it's very important that that collet body is screwed in first, nice and tight. Then that collet body sets in, then your back cap goes on, and then now it can adequately hold your tungsten. The last thing you put on is your gas nozzle. So once you put it together correctly, all you got to do is just release your back cap. Your tungsten will come in and out to sharpen it, put it back in, tighten it up, you're good to go. So again, that order of operations is very important to make sure that collet body threads, in other words, that collet body is tight before you do anything with that back cap and that collet itself that holds the tungsten. Hopefully that makes sense. So tungsten, it's our non-consumable electrode. So why tungsten? Tungsten has a very high melting point. And when we alloy that tungsten with alloys like cerium and lanthanum and zirconium and thorium, it even elevates their melting temperatures even better. So it makes them even better to use for TIG welding. So there's a certain bunch of tungstens that we use for different applications, and the size of tungsten really makes a difference as well. If I'm welding on really thin, low amperage stuff, I want a really small diameter tungsten. Because if I have a large diameter tungsten, the best analogy I can use is, let's say I got to fill a 5-gallon bucket of water. Do I want a simple 5/8 garden hose or a 6-inch pipe? Well, if I'm trying to fill that 5-gallon bucket with a 6-inch pipe, it's not going to work very good. But if I'm doing it with a garden hose, it's going to work good. electricity kind of works the same way. So the diameter of tungsten matters how much current you're going to be putting through it for what diameter you pick for your application. So there's acceptable amperages per diameter for tungstens. How you prepare that tungsten is incredibly critical. I think it's a variable that significantly affects precision welds. For most hand welding, it certainly has an effect on it, but for precision orbital tube welding or any automated type welding, how you prepare that tungsten becomes more and more critical the more and more critical your application. So different tungstens for different materials. So AC in alternating current, and we do AC for aluminum. So A, aluminum, I use AC. And what's like aluminum? Magnesium, very similar. So those aluminum and magnesium, we use AC to TIG weld them. All other metals, we typically use DC, direct current. So when we're on AC, there's a few tungstens we can use. We can use a pure tungsten, a seriated, a zirconiated, and a lanthanated. On DC, we can use a seriated, a thoriated, or a lanthanated. But look here, seriated works for both, lanthanated works for both. Seriated and lanthanated are what we want to use for advanced TIG welding machines. So there's no reason anymore to use pure tungsten. That's what we used for conventional machines. Zirconiated tungsten we used for conventional machines, and that zirconium would just elevate the melting temperature of the tungsten so I could use it for heavier amperage applications where the pure may not take as much heat and therefore liquefy on the end and do what we call tungsten spitting, where the tungsten goes into the puddle. So seriated and lanthanated work for both DC and AC, so why not keep an inventory of seriated or lanthanated? One or the other, they both work great. Thoriated, why not thoriated on DC? Simply because it's radioactive. And we'll talk about that in just a minute. So the classification for tungsten, you don't need to remember this. It's just showing you that E is for electrode, W is the chemical designation for tungsten, CE, the chemical designation for cerium, or La for lanthanum. There's thorium, zirconium. There's a G for general or unspecified, and there's a P for pure. So EWP would be the pure tungsten. And then the -2, it might be a 2, it might be a 1.5, or it might be a 1. It indicates the approximate percentage of the alloy addition. So, talking about all the different types of tungsten. So the first one is pure tungsten. Talked briefly about it. It's for conventional AC. It's mostly pure tungsten. It doesn't have as good a current carrying capacity as a zirconium tungsten would by comparison. We have 2% seriated. That's probably what we use the most. That's what comes with most TIG torches and welding machines when you buy them today, at least the advanced TIGs. Works for DC and it works for advanced AC. You can see its alloys with cerium 1.8 to 2.2%, and again 0.5% ends up being who knows what. But again, great for all metals. 1.5 lanthanated. It's pretty straightforward, same type of thing as seriated, except it uses lanthanum. And there's 2% lanthanated. And also these colors you see coordinate to the paint scheme used to identify these electrodes. So on one end, it'll have a dip of the paint color on it. So you never sharpen both ends of a tungsten. You only sharpen the one end, leave the other end painted on that color so I know what it is. Because I could line them all up with no colors on it, and until you welded enough and struck arcs with them, you'd have no idea what you have side by side to each other. And even after striking an arc with them, you still might not be able to fully tell the difference between seriated, 1.5 lanthanated, and 2% lanthanated. Then there's the rare earth electrodes, EWG. G are general unspecified. So this is where I have a very strong opinion in the industry. They sell you all these tri-alloy tungstens and all these whatever name tungstens. They may work great, but the problem is it's an unspecified way that it has to be made. So 2% seriated tungsten has to be made a certain way to be called 2% seriated tungsten. And I can have that repeatably from one manufacturer to the next. Well, with a rare earth in this case, or an EWG, it's general or unspecified, so the alloying agents, what they alloy with, how much of what they use can vary from one manufacturer to the next. So if I stick with manufacturer A and I use their tri-alloy tungsten and I'm on a big job and I have all my welding procedures specified out to it, and they can't produce that part for some reason and I have to buy it from manufacturer B, I might not have the same stuff, and therefore I may have a quality control issue that may be detrimental to my welding. So it's best to stick with the standards in this case until this EWG or this tri-alloy starts to get recognition and has a more specific way to identify how it was made and what's in it, so that I can ensure that I have consistency across one brand to the next. Because in welding code, I can't move from a 2% thoriated tungsten to a seriated or lanthanated without potentially requalifying my welding procedure. So why would I be able to just use these generic rare earths that could be anything from anybody? You don't know what you have. So it's just a difficult thing to control. 2% thoriated tungsten is great for DC. We can make some tricks to make it work on AC, but the fact is 2% thoriated tungsten is actually being phased out because it is very, very slightly radioactive in its dust format as well as when it's hot. So what are we doing with it? We're grinding it, making dust to sharpen it, and we're elevating it in heat because we're welding with it. So that slight radioactivity is enough that some companies like Northrop Grumman or some of the shipbuilding companies, they don't even let that stuff on the premises. Military contractors, they'll Geiger counter you on the way in and it'll set off alarms. So you don't want to, we're not using it anymore. It's going away. Still out there, you can still buy it. It's level, we're probably getting bombarded with more radioactivity just standing anywhere we are right now in the Phoenix area than we would be getting from this. But safety people and things are shying away from it. And in theory, they can actually make a thorium nuclear powered power plant. So it is radioactive. Zirconiated tungsten, we mentioned it before, it's just a way of elevating a pure tungsten, if you will, on a conventional old school AC machine so that I can get away with a smaller diameter tungsten and have more amperage going through it. So just to review, seriated and lanthanated tungsten, they're the best. The rest, don't really need them anymore. So preparing the tungsten, critical thing here. In the old days, they'd say take it, break it on the edge of a table, and you can see in the illustration here, it cracks. It might even split down the middle. I've seen brand new tungsten where literally 7-inch long is what it is. It was a 332 diameter. It fell on the floor. The whole thing split right down the middle. And that just happens to be that particular tungsten manufacturer did a bad job on that batch. So there's some tungstens are crazy. Sometimes tungstens don't even work in some applications. I had a customer had a brand new welding machine, said it didn't work out of the box. I show up, sure enough, it won't even strike an arc. Scratching my head, just like, what? This isn't right. So I took their tungsten out, I put my tungsten in that I had with me, it struck an arc every single time. Took my tungsten out, put theirs back in, wouldn't even strike an arc. So there's really 3 known good tungsten manufacturers that work with these advanced machines. There's Sylvania, which is supposedly made in the USA. It's a known good source of tungsten. There's a company called Diamond Ground that has very high quality procedures in place to ensure that they produce good quality tungsten. So Diamond Ground is another known good brand. And then of course Weldcraft, which is a sister to Miller. We also have my brain just shut off here. I got to back up. So the Weldcraft tungsten there was 10 Chinese manufacturers that made tungsten. We visited all 10 of them. We found one that had their act together. That's who Weldcraft sources it from. So just like Diamond Ground, Weldcraft has a very high quality standard to ensure that tungsten's good. Other brands, sometimes it can be a crapshoot. Just like I said, why? No idea. It's just the way it is, the way it's made. We've seen tungsten with porosity down the middle. We've seen it where you go to bend it and it breaks. You go to break it and it bends. I mean, just all kinds of crazy things with tungsten. So those 3 known good sources are important to understand if you're having a welding problem. That might solve the problem in some of these advanced TIG machines, because these advanced TIG machines are very touchy about how good that tungsten is, and how you prep it is just as important. So in these illustrations you can see that depth, 1.5 times the electrode diameter going back is actually a 30-degree included angle there. 4 times that length going back is a 15-degree included angle. So I like a 30-degree included angle for everything I TIG weld, so I highly recommend that 30-degree included angle An easy way to eyeball it is that that depth is about 1.5 times the diameter. It's very important that you grind it in the right direction. So if you're grinding your tungsten and the wheel is spinning this way on my tungsten, that's what I want it to do. I don't want to go sideways, and I don't want my tungsten to be aiming downwards. And the reason for all of that is electrons take the path of least resistance. So we want to get those electrons to come down off the end of that tungsten right where we want them to go. Because if I sharpen that tungsten in an incorrect direction, you can see it just might say, oh, there's a groove here that I'm just going to pop out that arc off of the side. So the smoother I grind it, the lengthwise that I grind it, the better off I'm going to be able to control where those electrons are coming off of that tungsten electrode. So here's another good illustration. So you can see 10 times the upper left corner. That's a 10x magnification of hand grinding it the wrong direction. On the right top is a 20 times magnification of the factory surface. So the factory surface is even ground in the wrong direction, but it's at least pretty smooth, so it helps. The next middle picture down on the left, 10x hand grind lengthwise. So you can see, if you look close there, you can see a lot of burrs and things. So those are little pieces of tungsten that could potentially fall off and get into the weld and potentially cause a failure in some critical applications. On that right image, you can see the 20x hand grind lengthwise, how deep those grooves are. Certainly it's in the right direction now, but they're so much deeper and there's burrs involved, may be a bad thing. For what we're doing in the lab, we'll be just fine. For your general welding, probably just fine. But critical applications, you need it like on the bottom. Using a tungsten grinder with its medium grit, you can see that so much cleaner, the burrs are gone, and that 20x magnification, you can see that it's even a smoother surface yet. Imagine the fine grind, it'd probably be just almost a mirror. But we use diamond ground tungsten grinders specific for tungsten to ensure that we don't have contamination from other things. So when I just take a tungsten and I sharpen it on any grinding wheel, whatever that grinding wheel was grinding might get embedded in my tungsten. So having a dedicated wheel or a dedicated tungsten sharpening tool is best. One thing to note too, a lot of people sharpen with just a bench grinder with a fine wheel, and they start getting deep grooves on that wheel. Well, those deep grooves are very dangerous. You need to make sure you dress that wheel with a wheel dresser that it's flat across all the time, and get in the habit of moving your tungsten side to side rather than creating those deep grooves, because those deep grooves could make that wheel actually shatter and just spit rocks all over your face and potentially into your eyes if you're not wearing proper safety precautions. So smooth wheel. Don't let the grooves get in it, but better yet, just have a professional tungsten grinder to ensure that you're doing it right. So when we're doing conventional AC TIG, we prep our tungsten where it makes a ball. A pure tungsten, you can see the green in the image. That ball shouldn't get any more than 1.5 times the electrode diameter. If it does, it'll actually get so liquid, it'll drop out into the puddle. Now you have a tungsten inclusion. So from the image, you can see the picture, the photograph is what typically happens in about a safe spot to keep it. On advanced AC though, and we're going to be talking a bit more about what advanced AC is, we want to sharpen it like we would for stainless steel to a point, except that we need to blunt it back a little bit so that little bit of blunt back will make the size ball that it needs based on all these other variables that we're going to be talking about. So advanced AC tungsten preparation, we previously talked about how smooth it needs to be and the grind direction. Now, same way I'd grind it for DC with a needle point, but just blunt it back. And where you blunt it back, just depends. So DC, straightforward. Sometimes in DC, they like to blunt it back. And the reason is that when those electrons come off of that tungsten, they come off generally at a 90-degree angle from the face of the tungsten. So different tungsten angles will give you different bead shapes. So you can see on the right, that 90-degree included angle actually makes for a narrower puddle, so it's concentrating a lot more heat into a small spot. Well, when I do thin stuff, I actually probably want to use that 15-degree included angle so that arc energy is spread out to give me more control on that really thin material, because if it's really focused, I'm punching a hole through it. But if it's spread out a little bit, give me a little bit more control to actually make a nice small bead. So this illustration is a great illustration of why that angle makes a difference. and blunting it back, you could think about it almost makes it even tighter than that 90-degree included angle will give you. There's an illustration, not the greatest of images, but you can see on the right is like a 90-degree included angle, on the left is like a 15-degree included angle, and you can see the shape that the weld bead made when those angles were changed. So in gas tungsten arc welding, we talked about a lot of the stuff to get up to this point, but now there's the difference is using direct current and alternating current. So let's talk about direct current quick. So in direct current, high frequency initiates the arc. Basically, it's done with direct current electrode negative, also known as straight polarity that we want to get out of our vocabulary. So DCEN is what we use to basically weld everything but aluminum and magnesium. So our tungsten selection, we can use seriated, lanthanated, and thoriated. Again, seriated, lanthanated, best choices. Our amp settings are just like all the other general rules of welding, about 1 amp for every 0.001 inches. Works great. So 1/8 inch, 0.125, roughly 125 amps is going to work to weld 1/8 inch. The key too is volts times amps times time is what melts that puddle. So I can weld at 75 amps a lot slower, or I can weld at 125 amps and go quicker and get the same results. So higher amperages are needed for copper alloys than this chart explains, but for this, that 1 amp for every 0.001 inches seems to work for everything except copper. So when we're in DC, there's a couple of arc starting methods. So there's lift arc, where you literally touch the tungsten to the work, and I lift it up and it strikes the arc. And then there's high frequency. High frequency is a very high voltage, very low amperage, and voltage being electromotive force that jumps an air gap. So that high voltage, high frequency jumps the air gap and then has a path for the low voltage, high amperage welding arc to ride to jump that gap to strike that arc. So high frequency is a great tool, but it can also take out computers and more sensitive components. So sometimes using tools like lift arc are a great thing in DC to start that arc. Another reason for lift arc, there's old school scratch start. So when I took an old school stick welder and I hooked a TIG torch to it with gas hose to it, that old machine had about 80 open circuit volts. So I would do scratch start TIG like you did for stick welding, but you had to be extremely careful because you don't need that tungsten to break off or stick to the part, because they need to have a tungsten inclusion and now a potentially rejectable weld. So they invented lift arc. And what lift arc does is it takes it to about 8 open circuit volts with 0 amps, and the machine can sense, oh, you're dead shorted. I can turn on the amperage now, and it just times it out perfectly so it's not sticky, and you can get a good arc start by having to touch the tungsten to the work without contaminating the part. So this chart that we're going to start filling in, you're going to want to pay attention to when we get this third column filled in, but in direct current electrode negative is the key that we use for all metals. And what happens is we say that electrons flow from negative to positive. And in this case, the oxide removal action we'll be talking about later doesn't happen in DC electrode negative. And the heat balance is about 70% of the heat happens on the work, and about 30% of the heat happens on the tungsten. So the general bead width is narrow, and the tungsten capacity or longevity is great. An 1/8 inch tungsten will carry 400 amps with direct current electrode negative. This is great for welding everything but aluminum and magnesium. I can do aluminum, there's ways here, and it works. Just like in all welding, there's 10 ways to skin the cat, but in some things are just better than others, and in this case, electrode negative is great for everything. So aluminum oxide melts at about 3,600 degrees Fahrenheit, and the aluminum underneath melts at about 1,220 degrees Fahrenheit. So we can never truly remove that aluminum oxide unless I was in outer space or in an argon bubble. I could maybe wire brush and move it away, but aluminum oxide forms almost instantly, and you can never get rid of it. You can only really thin it out. So that's where we use direct current electrode positive. So electrons and ions are flowing in the opposite direction. You can see there's a little bit of etching zone or white around the edges. And that electrode positive actually removes that oxide off of an aluminum, for example, and its heat relationship is the 70-30, but in this case, 70% of the heat's on the tungsten and only 30% is on the part. So now the tungsten is going to melt a whole lot quicker, gives me a wider bead shape, and its capacity is horrible. A 1/4-inch diameter tungsten will only carry 120 amps. So DC electrode positive, not very good for welding TIG. DC electrode negative, great for TIG welding everything. But this leads us into AC. So backing up quick to that slide, the difference between electrode negative and electrode positive, well, that's actually AC, because half the time it's negative, half the time it's positive. That's essentially what AC is. So current alternates from positive to negative 60 hertz, or 50 hertz in Europe. So that means basically one positive and one negative cycle 60 times per second. So it literally changes 120 times per second, right? Because 60 positive, 60 negative equals 120. Changes. And that's per second. So what does AC do? Positive side of the AC has that cleaning or etching effect on the material that we just talked about on the oxides, and the negative provides the heat to the part. So that's why we use AC for aluminum, because that heavy oxide layer exists, and that electrode positive gets rid of that oxide layer for me, so I have a good, clean, beautiful weld that's minimized how much oxide is there. So, but if I do it with just DC electrode positive, I'm using giant tungstens. It's taking forever to heat the part. I'm getting oxide out, but I'm not putting a puddle down. So I need to throw some negative in there to put some heat on there to get the puddle there, but I need that positive to clean and etch it. So the other thing about AC is because it does those changes, 120 of them every second, the arc literally shuts off and turns back on. So we use high frequency all the time on conventional AC welding. And the illustration here, you can see the green line is an AC sine wave for a welder, for a welding arc. The black line that's high hertz that you can see is high frequency. And that allows me to transition through that off point that the arc turns off and turns back on 120 times a second. So high frequency is used to maintain and stabilize that arc, and it's continuously used on transformer machines. And contrary to popular belief, it does not clean or etch or get rid of anything. It doesn't create that white etching along the side of the weld. It affects it, sure, but that's not what's creating it. High frequency only stabilizes and starts that welding arc. Has no other purpose in the welding, in the AC welding arc. In DC, high frequency only starts the arc and it shuts off. In conventional AC, it's on all the time, and in the advanced AC, it's only on to start the arc, and we'll see why in a little bit. Tungsten selection for conventional AC, pure and zirconiated. We can use the seriated and lanthanated too, except when we use the seriated and lanthanated on conventional AC machines, we have to switch our machine to electrode positive and strike an arc and make a really big ball on that tungsten, then go back to AC to weld with it. Not so on advanced machines where pure tungsten makes the size ball it needs based on the current it's carrying, so that's why pure is so good on conventional AC. So materials that are welded with AC, as we mentioned before, aluminum, magnesium. And this chart right here is what you're going to want to remember. You're probably going to want to take a screenshot because you're going to see this again. But the important stuff here is that in the AC balanced column, and when we say balanced, that means half the cycle time is electrode negative, the other half the time is electrode positive, and they're both hitting the same amperage level. So if I was welding at AC 100 amps, means half the time it's negative at 100 amps, half the time it's positive at 100 amps. So every half cycle I get my cleaning action, or my oxide removal. My heat distribution now is balanced between the two, so it's 50-50. So 50% of the heat's on the tungsten, 50% is on the work, and my bead width is somewhere between the electrode negative and electrode positive arc. So the bead shape is somewhere between these two scenarios, and the electrode capacity is also somewhere between, where an 1/8 inch tungsten will carry about 225 amps. So understanding this chart right here is really the key to understanding the advanced TIG welding. These advanced machines have some more controls on them for AC, and for me to understand the difference here. So, still talking about AC and this zero crossover is in sine wave. This illustration here shows you literally how that arc shuts on and off and why we need high frequency to strike that arc. In this illustration too, you can see here in this video, there's etching, now it's not etching. There's etching, not etching, etching, not etching. And during that etching zone, you can see the little tiny kind of sparkles happening on the surface of that weld. And those little sparkles, that's the etching that's occurring that creates that white zone on around the weld. The other half is the actual welding arc heating that part up. And in this video, I'm not sure, I can't recall if it actually shows an arc outage. I do not think it does, but sometimes the arc will rectify and go out. So arc rectification happens when one half of those cycles misses. So you can see an oscilloscope type drawing on the left that you can kind of see where the positive half of that arc, for example, in here is showing that it's fading out where it's going to miss half that cycle. So we use high frequency all the time to avoid that from occurring. Then we talked about that big advanced thing that happened in 1976 where we created a square wave AC arc. This was the monumental thing. If you see in these two illustrations, you can see the big difference between the sine wave on the left and the square wave on the right. On the sine wave on the left, you can see the arc, the amperage rise in and peak out and then slowly back off, shut off, reestablish itself, rise up, come back down, shut off again, where on the square wave side, you can see it almost instantly make that transition through zero. So for you calculus guys out there and gals, this is where area under the curve comes into play. So if you look at these two, the green line is our square wave AC shape, and the blue dotted line is our sinusoidal conventional AC wave shape. You can see that there's two different areas under that curve, and the one with more area is putting more energy into my part. It's actually letting me weld more efficiently. So the square wave was monumental in AC TIG welding, and it made that arc so much more stable, had more energy there. I could weld better, longer, and just make more money. So back to that AC, balanced AC wave, this is where, in this illustration, you can see a lot of white etching along the toes of the weld. You can see a pretty large diameter ball in the tungsten. So 50% of the arc time is positive, 50% is negative, and it makes a medium bead shape. It's somewhere in there. Then on a conventional machine, I can go to this max cleaning setting where it's not cleaning anything. It's not cleaning oil, grease, dust, dirt, debris. You had to do that prior. This is etching the oxide layer. So that name cleaning is going away, and it'll say maximum etching. But this is where I now have what we represent as percentage electrode negative. So here I had 45% electrode negative. You can see the ball in the tungsten is bigger than the previous slide. You can see that the white etching is even more predominant than the previous slide. And then here on the maximum penetration, which again, penetration is a poor word. It should say just percentage electrode negative. It should be the general name here. But it's not creating how much penetration into the part, because penetration is a function of volts times amps times time. Can't repeat that enough to understand that. But in this case though, when I turn this to 68% electrode negative, you can see that there's a lot smaller ball in the tungsten now. The etching zone is reduced. I'm putting more heat on the part, and I'm minimizing how much of that etching is occurring. But now we get into this advanced AC. So that was the conventional basics that occurred from AC to DC and TIG welding in general. So inverters for gas tungsten arc welding change everything. They give us extended AC balance control, and we're going to be talking about all these quick. Extended AC balance control, AC frequency control, waveform selection, independent amperage control, pulsing capabilities way beyond a transformer machine, easy power hookup, low-end arc control, precision arc control, complete process control, advanced arc starting, program memories, parameter locks, advanced automation features, smaller, portable, more machines give you more capabilities to take you more things. This is why these inverters we talked about earlier are killing these old conventional machines, because I could do all this stuff with these that I could not do with everything we explained up to this point. So in AC, I have AC output frequency control that adds focus to the arc and tight fillet joints. We have 4 separate AC waveforms. A sine wave is old machines. We have a soft square wave, which is current machines. Then we have advanced square wave and triangular waves. We can set our new machines to use any 4 of these wave shapes. This is that transition on how it goes from positive to negative, and this is that area under the curve thing. How that wave shape is made significantly changes how that AC arc lets me weld aluminum so much more efficiently. I have independent amperage control, so I can control how much amperage I'm on the positive half of the cycle and have it be a different level of amperage on the negative half of the cycle. I can take that balance control we just talked about that went from 45 to 68% electrode negative. Well, now I can go from 30 to 99% electrode negative. So now I can really start to take advantage of that electrode negative half of the cycle that's putting heat in my part, but just use enough of that electrode positive half of that cycle to let me etch that oxide layer out of the way. So in this inverter technology gave us this advanced square wave AC. It's almost a perfect square now. So we're utilizing that energy even more efficiently. It's giving that arc shaping capabilities with improved balance control. So when I decrease my percent electrode negative is increased, I get a narrower bead and I get a little more energy going into the part. When I use more electrode positive in time, just like before, I might have a little bit wider bead, but I'm getting a whole lot more etching going on. So I can really start to shape that bead by changing the balance control more so than I was with a conventional machine. So here you can see in the illustrations with a lot of electrode positive, I get a lot of etching going on. Even onto the surface of my bead, I have a large ball in that tungsten, so there was a lot of heat going on the tungsten. When I went to electrode negative, you can see there's almost no etching zone, and that tungsten is almost sharp like a needle. So that gives me significant control between these two. The beads might look the same size, but they're really not. Probably both are the same 332 diameter tungstens, so if you really started scaling these images, you'd probably see that bead is certainly more narrow on the electrode negative one than it was with the electrode positive image. I have frequency control now. Now, instead of my machine being limited to my operating frequency of 60 hertz that comes out of the wall, or 50 hertz in Europe, I can actually take this machine and I can go down to 20 hertz, which will widen that arc significantly. I can go all the way up, depending on the machine, up to 400 hertz, which will actually focus that arc significantly. So by changing the AC frequency on the output of the machine, I can have a huge effect on my bead shape and profile and the control of that arc. So frequency is probably the easiest and quickest way to see a big change in shaping that arc or bead shape. That electrode positive and electrode negative balance is another way to control that arc. So looking at frequency adjustment, a great visualization is, here's a T-joint, 3/8 wall. You can see in this illustration some incomplete root penetration in the corner of that weld joint. We have to break down that very corner. Well, this is easy to get in an old school machine, and this video shows why. With that large ball in the tungsten, this is high-speed video, that AC current going from positive to negative, that electricity is taking its path to least resistance. So in this case, off the end of the ball, it's going wherever it wants off the end of that ball. I really don't have the directional control and stability to ensure that I'm directing my heat energy where I need it to in that puddle. So when I go to my higher frequency adjustment, you can see it's a lot easier to break down that corner, and this video is the best illustration. You can see now I have that sharp tungsten, I have a high hertz, I have more electrode negative, and I'm able to really focus that arc energy and direct it exactly where I need it to go, as opposed to the conventional way. This right here is probably the best illustration to see why you want to have an advanced TIG machine versus a conventional TIG machine. Because if you're doing aluminum, this is huge, very important stuff. So these waveforms also affect this to another scale on a smaller scale. So there's a sine wave AC, and you can see in the high-speed video, this high-speed video and the 4 high-speed videos you're going to see are advanced TIG machine. They are 150 amps at 120 hertz with 70% electrode negative. So 70% of the time it's dwelling on the negative half of the cycle, and 30% of the time it's on the positive, which you can see by the etching happening on the surface, the little sparkles. And it's happening at 120 hertz, so it's on and off pretty quick. So backing up to the sine wave, the benefit of the sine wave is it's a soft arc. It simulates old school conventional AC welds. It's very soft, it's sluggish, it's not as efficient. You're going to put more heat on the tungsten, and you can see in this waveform design though, it's not a true sine wave, because we have to trick it a little bit in that zero transition so that it almost instantly makes its transition through zero so that it reignites without having to use high frequency on all the time. That's the benefit of these new machines, these advanced machines. We don't have to have the high frequency on all the time to keep that arc stable. What these machines will do is, because they can see it and react so quickly, they'll throw a burst of high frequency in there if they think it needs it. Why do we want to eliminate high frequency? Well, high frequency can be really annoying in a welding shop because it can cause the phone lines to do all kinds of crazy stuff. It can cause computers to do crazy stuff. There's even companies that are near airports and the FAA comes knocking on their door saying, "What are you doing?" Because high frequency is actually a radio broadcast and it can interfere with the communications. So they have to do all kinds of precautions in buildings like that when they use too much of it. So AC, these advanced machines don't need high frequency all the time. They only use a burst when they need it, or they only use it to start the arc. And so that's why this waveform is a little modified from what would be a conventional sine wave. Then there's this triangular wave. It's just like a triangle shape, makes that transition through zero pretty fast. Great wetting action, minimal heat input, and it can reduce distortion. At high frequencies, it can actually become very digging and aggressive. There's actually companies that use it to try to cut into a part before they weld it. Kind of crazy. But another place that it's awesome is in the aerospace industry. Aerospace welders have to do an extremely thin wall T-joint weld test in the vertical position. And they have these big fixtures that are heat sinks, and these heat sinks just take all that AC away. Well, when I use that triangle wave, that instant in time that it's at a high amperage just punches right into that corner to get that root penetration that I need without overheating it, because on these aerospace tests, not only do they got to get into that corner perfectly, they can't melt through the backside at all on the parts. So with a conventional machine, it would take them forever to get the whole fixture hot, the whole part to get hot, just to try to maintain this tiny little puddle that gets adequate penetration without getting too hot and melting through. Very difficult test. They would take 10 to 20 of these tests to get one right. But with the triangular wave, it actually makes it so easy they can just get right on it and they're done. It's a beautiful thing. So that instant that it goes to that high, to that peak amperage, if you will, it's just enough to punch it into that corner. And being that triangle shape, there's a lot less energy there. So we lower our heat input, but we get that benefit of that quick punch of high amperage to just get in there quick. So, and again, at very high frequencies and higher amperages, becomes digging and aggressive. Then there's an advanced square wave where the only way I know how to describe it is it's just, it's there. It's just, I don't know how to say it any other way. The arc is just, it's perfect. It gets into that weld puddle just like you want it. It's a perfect square. The energy's there. It's digging and aggressive. It calls it a little bit. It's an aggressive arc. Great directional control. Our old Aerowaves and initial Dynasty type machines used this only, but today it's an option. And it's actually not our default option anymore, but it's an option in the pocket when you just need an arc that can just punch in there. Just, I don't know how to say it any other way. Then there's a soft square wave, which is like our conventional square wave AC. It's a less aggressive arc. Get all your enhanced puddle controls and wetting action. It's the factory default waveform today. It's the square wave AC that you find in a sinker wave. It's the square wave AC we find in our advanced machines, and it's a great arc. It's probably the best arc to start with. It's a beautiful thing. It does a great job. And then this slide, here you can see all four of those waveforms happening at the same time, just as a little bit of a comparison to see how they're making that transition through zero. And again, keep in mind, all of these were all 150 amps. They were all 120 hertz, and they were all 70% of the cycle time on electrode negative. and they were all equal positive and equal negative amperages. But just something interesting to kind of see them all together on how they're making that transition. You can see on a couple of these, there's kind of this weird, when it makes the transition, there's this weird little kind of stabilization that happens. Just kind of that overshoot of going through that transition through zero so fast. A lot of crazy physics going on, probably a lot of unexplainable stuff in here too. And then the final feature really is independent amperage control. So we talked about on these advanced AC machines, a conventional AC machine today gave me balance control. I could move that line left or right. Then it gave me frequency control, let me move that line even more so in these new machines. Then it gave me frequency control on how many of them are happening per second. Now it's giving me the control to say how much is on the positive half of the cycle versus the negative half of the cycle independently. So on the image on the left, you can see we used a lot of electrode negative amperage, equal time, sharp tungsten, minimal etching, because that positive half etches the oxide layer, the negative half puts the heat on the part. It's all about finding this balance that works for the part, how clean the part is, the aluminum alloy you're running, but it makes you a more efficient aluminum welder. On the right, you can see a lot more electrode positive amperage. You can see the tungsten got a little more melted, and you can see more etching happening. And both these welds were made with zero high frequency, so debunking the idea that high frequency creates that etching. It's all about the electrode positive that creates that etching. So that independent amperage control, you can just see from the previous illustrations, here's another way of looking at it. But we're changing how that bead shape happens. More electrode negative will tend to make it a little bit narrower, and electrode positive will make it wider but with a lot more etching. So AC TIG review from the old school sine wave ACs that really don't exist anymore. You had a sine wave, you had a ball in your tungsten, you used high frequency all the time, and you had no balance control. It was 50-50 AC. Then in 1976, that conventional square wave AC came. Now it gave me that more square shape, utilizing the energy more efficiently. I used a crowned tungsten, so it doesn't make as big of a ball. I use high frequency continuously still, but now I had balance control, and that balance control was limited, but it was certainly better than 50-50. Then came along these advanced square wave ACs that use a true AC square wave shape, but also the options to do others. I use a sharp tungsten rather than a ball. I high frequency only to start the arc rather than have it on all the time. I have the extended AC balance control from 30 to 99%. I have that AC frequency control from, instead of that limited 60 hertz, I can go down to 20 hertz and widen my arc, go up to 400 hertz and focus my arc. I have independent amperage control to control how much energy is going into that part to help me to make that weld as efficiently as possible, whether it's in shape, whether it's helping to do certain alloy things, whether it's controlling how much heat is in there for heat treatability. So much more capability than ever before. So here's another way of seeing some of these things. So a conventional 300 amp machine, was limited to about 1/2 inch aluminum. So the same 350 amp advanced machine will give you 3/4 inch aluminum. The continuous high frequency on the old machine will start only for the new machine. Lets me use things with, lets me actually maybe even weld on the new F-150 with aluminum body. I'm sure Ford will say, no, do not TIG weld on the body, but that's because they're not thinking about the fact that on these advanced TIG machines, I can actually do AC with lift arc mode where there is zero high frequency in that circuit, because they're paranoid that high frequency is going to wipe out a computer on board of these vehicles. And as you might know, a vehicle computer isn't cheap. But anyway, eliminating that high frequency might be an option for unique applications that are near sensitive components that we need to eliminate that high frequency. Or again, we're drastically reducing the use of it by having it only on the start of the arc. We have our output control from being fixed at 60 hertz. Now we have variable from 20 to 400 hertz depending on the machine. Some machines are limited at 250, others limit up to 400. But 20 is the bottom, 400 is the top of the range typically available. Lets me focus that arc, punch it into the corner on a fillet weld, or make a smaller weld, whatever I might need. Conventional machine had that soft square wave. Well, the new machines, I got all 4 wave shapes to pick from. Again, it's a heat energy thing. What works for my application? What gives me a better result as to make my weld as efficiently as possible. Instead of a ball on the tungsten, we use a point on the tungsten. Our portability from 496-pound machine, we can go to a 108-pound machine. Big difference. And the conventional machines would only operate on single phase, and they need a lot of amperage to operate on single phase. Like 110 amps at 230 volt single phase drew a lot of amperage. But a inverter machine, I can run 32 amps on a, I'm going to draw 32 amps on 230 volt three phase. So I'm not even going to pay my power company as much money, but I also have significant more flexibility in what I can plug it into on different job sites. So having that significant range of different things that I can plug into and being able to plug it into three phase saves me money in electricity. There's one area in welding that an inverter on AC TIG welding from conventional machines can save you a ton of money. Quick example, a 200 amp TIG machine, sine wave that we used to make, or I'm sorry, a square wave, it wanted a 90 amp breaker, where a 200 amp inverter wanted a 30 amp breaker. It's a big difference for its full output of the machine. Precise controls, old machines had some digital settings, but how did I know my balance? It was just a knob, like I dialed to 3 to get 50-50, but how did I know I was at 50-50? Well, in these advanced machines, we have all digital readouts, so now I know I'm at 75%, 72%, 71%. Now I have good repeatability because I have a digital dial to tell me where I'm at, so I can have more accurate repeatability having those digital controls. Then we have AC balance control. 45 to 68% electrode negative, and on the new machines I can go from 30 to 99% electrode negative, so much bigger range to really balance and optimize how much heat we're putting into the part and minimize how much etching we need to do, because etching just gets that oxide out. The rest is helping me weld a little bit more efficiently. So pulse TIG welding fast with an inverter reduces that overall heat input. So by pulse welding with TIG, we can kind of think of pulse welding similar. We have waveforms, like we just talked about all these AC waveforms. Well, pulse welding is typically used with DC welding, not with AC. And on DC, we use it for materials like stainless steel, titanium, Inconels, and Hastelloys. But by pulsing that current hot, cold, hot, cold, hot, cold really fast and using an inverter, I can control it from 0.1 pulse per second up to 5,000 pulses per second. Why would I go to 5,000 pulses per second? Well, a tube mill that takes flat sheet and turns it into a stainless steel tube, they actually just roll it out, and actually they'll use a 5,000 pulse per second, 700 amp DC inverter TIG welder to fuse that edge when it gets forced together. So it's an autogenous weld with no filler rod, and the pressure together creates the slight bulge of the seam of the joint, and they TIG weld it, and that pulsing actually focuses that DC arc more so that it really puts that energy where it needs to be to make things like a tube mill. Low pulse frequencies, let's say around 1 pulse per second, there's my example for you. And I can actually just kind of time my filler rod adding with that, and I could use it for maybe a learning tool. 10 pulses per second is actually a pretty good pulse per second setting for things like Inconel and Hastelloy, where they have this real hard, heavy surface tension. They're very sluggish. But when I pulse them, it actually makes it easier to weld them. The best example I could give you, and you'll see it in lab at some point, is if I do an outside corner stainless steel TIG weld, and I'm doing really thin stainless, the only way I know how to describe it is it's like going from this, where I'm really focused, where I gotta be everything perfect when I'm steady, but if I turn that pulser on, I can actually relax a little, and it's a lot easier to make that weld. That hot, cold gives me enough control to melt that filler rod, but that low amperage side keeps that bead nice and small, so that hot and cold just gives me more control to make a nicer looking weld. Again, it's like going from being really focused, all hunched over, tight looking, to actually being able to relax a little bit and make that weld more efficiently. So pulse welding can be pretty nice. You get a narrower bead, you get a narrower heat affected zone, you have a much more focused arc, and again, you get rid of that surface tension off of things like Inconels and Hastelloys. So it's just an illustration showing some of the things we look at in pulse welding. So, 1 one pulse is basically it's 50% on or 50% off time in these illustrations. Next to it, you can see 4 pulses per second by comparison. So you have a pulses per second adjustment. Then you have a percentage on time adjustment. So in other words, 80% of that cycle time, it's on the peak current level. So then 20%, it's on the background amperage level. So there's a peak amperage and a background amperage that you adjust as well. So understanding what you're adjusting and having that repeatability to find those spots significantly controls how your weld is affected. Again, pulse, kind of like all that AC stuff, affects the narrowness of that bead, the shape of the profile of the penetration, getting rid of sluggish stuff off of the surface. Pretty neat stuff. So conventional pulse TIG, again, typically from 1 to 10 pulses per second on old school machines, but the inverters give me that 0.1 to 5,000 pulses per second. And basically when it becomes more than 40 pulses per second, it's more audible than visible. The human 60 hertz looks like continuous on, but literally these lights are flickering 60 times a second. After, somewhere in the neighborhood of 40 pulses per second or 40 hertz, I would see lights blinking if they were all operating at 40 hertz, potentially. So that's why lights are at 60 hertz, so that we don't see them blinking, and it becomes more of an audible thing in pulse TIG than a visual thing because I can't see it flickering anymore. But those lower pulse per second, I can actually see it flickering. Same with those AC hertz, that 20 AC hertz, I can actually kind of see that there's an on-off thing happening between the positive and negative polarity. So at the higher frequencies, it's audible, not visible. Again, changing the pulse frequency changes how focused that arc bead is. Higher hertz, more focused; lower hertz, less focused. The pulse TIG controls, again, we don't need to cover this too much, but low speed pulse, you get distinct ripples. High speed pulse, you get narrow beads, a lot tighter together. So things can go wrong in welding. Well, you can see in some of these images, welding with direct current polarity on aluminum. You can see there's a lot of heavy oxidation on that aluminum surface. It's terrible. Some smoke kind of happening because we're burning off stuff. Bad news. The middle one, you can see there's too much amperage. So you can see the solidification of that puddle is very kind of V-like. So the center is solidifying a lot slower than the edges, therefore potentially causing me cracks down the middle of the weld. The gas flow rate too low at the bottom, you can see there's little speckles all over the surface. That could be contamination of the gas or a lack of gas, but either way, too low of a gas flow is a bad thing, or not enough argon in this case is a bad thing. So the gas flow issues, again, may not, the gas is not on or the proper flow is not met. You haven't got the proper standard cubic feet per hour flow rate set, or your gas line is kinked. And the gas line can kink pretty easy because in TIG welding we tend to sit down. And we sit down with chairs with wheels on them, and we tend to roll around on those wheels, and those wheels actually roll over the gas hose on the TIG torch. They might even roll over the water coolant line on the TIG torch, cause my TIG torch to burn up. So I got to be really careful where my TIG torch hoses are, so I don't kink that gas line or that water coolant line to keep that weld quality up. Maybe your gas line has a hole in it, acts like a carburetor, sucks in atmospheric pressure, and now you have contamination coming in. Moisture in your gas line, that could happen too. Fittings aren't tight enough, therefore again, drawing in atmosphere. Maybe there's a breeze where you're welding in a fan. Got to be careful where that fan is blowing. Too much gas flow, also bad because it can create a Venturi effect and actually suck in atmosphere. Tungsten contamination, that can be a bad news thing. Dipping your tungsten in the puddle or your filler rod. Incorrect tungsten extension, so how far you're sticking it out of that from the gas nozzle. Typically you don't go more than 3 times the electrode diameter out of that gas nozzle. Any more than that, you're starting to get too far away. There's certainly exceptions to that rule, but don't want to stick that tungsten out too far or you start to lose how much shielding gas is protecting not only the tungsten, but protecting your weld pool. So not enough post-flow is a bad thing as well with tungsten because the tungsten is getting elevated in heat, and if that post-flow gas, if that tungsten isn't allowed to cool enough before the atmosphere hits it, the surface of that tungsten gets contaminated, and now you're potentially introducing those contaminants into the weld pool, creating a less than sound weld or a rejectable weld. So making sure you have enough post flow is huge. Another thing that happens in TIG is we have such a low flow rate that people stop welding and they drape their torch on something, and just that wind kind of blowing by could cause the shielding gas to blow away for a moment and contaminate the surface of that tungsten. So got to make sure that tungsten gets cooled enough from the post flow of that gas shielding, keep that tungsten intact. Dirty material is a bad thing that can cause contamination of your tungsten and your base metal. And again, dirty material, grease, oil, dust, dirt, debris, rust or pitted material, thick mill scales, oxide layers, they all have to be eliminated off your weld. The first 10 rules to TIG welding are clean, 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 clean. That's the first 10 rules. It's got to be clean. Got to get rid of that mill scale. We need to sand that mill scale off. Any rust, got to get rid of that rust. And oil, bad news no matter what. Other things that can go wrong, here you can see incorrect balance setting. Too much electrode negative may be a case where you have such a heavy oxidized material, you're not using enough electrode positive to help get rid of it. But that tungsten melting back into the cup means your tungsten's maybe too small for the amperage you're carrying. Maybe your balance is set to have too much electrode positive, or maybe your polarity is on too much electrode positive for your amperage on that side. Or maybe you just didn't go to AC by accident. So if that tungsten melts back into the cup, it's too much electrode positive some way or another. The weld bead has a dirty appearance. Well, again, you didn't clean it enough to begin with, so get rid of that stuff. Or you may have too much electrode negative for the level of oxide that you have there. There's TIG in a nutshell. Hopefully that works for you. There will be a quiz on it, so watch for it on Blackboard. And I hope these video series work while I'm on the road.